Swayam Prabha. Digital India. Educated India.
Welcome back to the third lecture on the topic heat and work transfer in flow and non-flow process, the subject thermodynamics and thermal engineering. So before going into see the contents of the today's lecture number 3, let us have a small recap that what we have discussed in lecture number 2. In lecture number 2, primarily we focused on thermodynamic process, how to define a thermodynamic cycle, what is the path of a process, application of zeroth law of thermodynamics, because it forms the basis for temperature measurement, how the first law of thermodynamics was postulated for a system undergoing a change of state for a thermodynamic cycle, and we solved few numericals. And in this lecture we are going to see the heat and work transfer in a flow and non-flow process. So the outline of my presentation for today's lecture is, first we will see what is a steady flow process, then the steady flow energy equation, it is called SFEE, steady flow energy equation, applications and few solved examples. What do you mean by a steady flow process? So as you see this one, so this is normally used for an open type of system, that is for a control volume. Whatever the mass which is going in, it comes out of the system, that is according to the conservation of that is the mass balance, like total mass flow rate in a system, open system, remains constant with respect to time. That is, total mass entering into the system should be equal to the total mass leaving the system. There is no difference between the mass entering and mass leaving the system. However, the volumetric flow rate of that fluid, need not be equal to the volumetric flow rate of the fluid which is leaving the system. It is the mass quantity which will be equal, that is mass in is equal to mass out, volume in need not be equal to volume out. The total energy content of the system remains constant. Let us take a small example. There is a system, there are 3 mass quantities, M1 10 kg, M1 and M2 are entering into the system. So this is the mass which is entering into the system. This is another mass which is entering into the system, and this is the one which is leaving the system. So if you apply the steady flow, if you apply the mass balance of this for this example is M1 plus M2 will be equal to M3. M1 plus M2 will be equal to M3. That is 10 plus 5 is equal to this one. So irrespective of the number of mass quantities, whatever the mass entering into the system, the sum of all the mass quantities entering into the system will be equal to the sum of the mass quantities leaving the systems. So if a system has several, here I have taken only 2 quantities of mass entering and 1 quantity of mass leaving. So in case if there are several input, inlet and outlet, then the mass balance is summation of mass entering into the system will be equal to the summation of the mass leaving the system. Now let us, with this background, let us see what is this steady flow energy equation. So consider a steady flow process in a system which has 1 inlet and 1 outlet. That is, whatever the mass which is entering in the form of M1, it is leaving the system in the form of M2. So this is the inlet, mass entry into the inlet, this is the mass entry to the outlet. So we have seen in the steady flow process that the total energy of the system remains constant. So this is called energy balance. Energy in is equal to energy out. Here the energy transfer is by heat, work and mass. Now I have taken M1 equal to M2 as equation number 1. and the energy balance equation as equation number 2. V1 square by 2. See, this is potential energy at the inlet, this is kinetic energy at the inlet, this is the enthalpy at inlet, that is the energy content of the fluid, this is the enthalpy at the outlet, that is leaving the system, fluid leaving the system, energy content of the fluid leaving the system, this is the kinetic energy at the outlet, and this is the potential energy at the outlet. So, m I have taken outside the bracket. So, m into G into H, instead of H, since we use the terminology H for enthalpy. So, normally H is used for enthalpy and Z is used for the datum or height. So, m into G into Z1 is the potential energy, m V1 square by 2 is the kinetic energy at the inlet. Similarly, here m into V2 square by 2 is the kinetic energy at the outlet, and m into G into Z2 is the potential energy at the outlet. So, this is the Q plus this one. So, this is what of the this is based on the energy entering into the system, which is equal to energy leaving the system, E in is equal to E out. Now, I have taken this as equation number 3. This is equation number 3. Divide this equation by m. So, here you will get Q by m, here you will get Q by m, this m term will get cancelled. Similarly, this m term will get cancelled, and here I will get W by m. So, dividing the equation 3 by m, I am getting this term. So, this capital Q by m I am using small q, and capital W by m I am using small w. Remaining quantities I have written H1 plus V1 square by 2 plus G Z1 is equal to H2. There is no change. This is equation number 4. This is equation number 4, where small q is equal to capital Q by m and small w is equal to capital W, or the heat transfer and work done per unit mass of the working fluid, per unit mass of the working fluid. Equation number 3 and equation number 4 are the two forms of steady flow energy equation. So, depending upon the conditions which are given in the problem, we can apply either equation number 3 or equation number 4. Now, let us see some of the applications of the steady flow energy equation. In the lecture number 1 itself, I have told most of the engineering systems or devices are of open system, open type, that is wherein both mass transfer as well as energy transfer takes place. They are not closed system, most of the devices are of open, like you take compressor, turbine, heat exchanger, you take any refrigeration device, air conditioner, all those things, all these are typical examples of open system. So, some of the applications which we will be seeing in this lecture are nozzle, diffuser, compressor, turbine, heat exchanger and throttling device. Nozzle is a device which is used to enhance the velocity of the fluid. So, if you take a nozzle, it has no moving parts due to the varying cross sectional area, as the fluid enters with a low velocity. By the time it leaves the nozzle, its velocity is enhanced at the expense of pressure. Of course, pressure drop takes place. So, this is just the concept of this Bernoulli's principle. Diffuser is just opposite to the nozzle, whose function is to increase the pressure at the expense of velocity. So, the diffuser, the fluid velocity is high at the inlet, at the outlet the velocity is reduced, of course, the pressure of the fluid will be increased. So, nozzle and diffuser perform exactly the opposite functions. Compressor and turbine, if you take compressor is the one which is used to compress the fluid, especially the gas. Compressors are designed for handling gases and air and not for liquids. of course, pumps are used for handling liquids. If you take the isentropic compression, which is just exactly opposite to the isentropic expansion. So, these are all compressors are power absorbing devices, and turbine is a one which is a work producing or a power producing device which is used in power plants, etc. And heat exchangers, where there is a heat transfer between two fluids, there is mass of each fluid, both the fluid, cold fluid, hot fluid is involved. The temperature, hot fluid temperature is reduced, cold fluid temperature is increased. So, obviously, there will be change in the enthalpy, all those things and all. Throttling device, of course, is the one which is used. It could be like an expansion device, which is used in the refrigeration, vapor compression refrigeration system or an air conditioning system, which is used to reduce the pressure between the condenser and the evaporator. So, this primarily in this steady flow energy equation topic. So, the numerical, the practical, how this equation is applied in the various real time applications, we are going to solve some problems. So, let us see the first numerical. Air at a pressure of 1 bar and 7 degrees centigrade is compressed to 6 bar and 127 degrees centigrade. The mass flow rate of the air is given, that is 0.02 kg per second, and a heat loss of 16 kilojoule per kg takes place during the process. So, during the process, for every 1 kg of air, there is a loss of 16 kilojoules of heat. Assuming the changes in kinetic and potential energy are negligible, determine the power required to drive the compressor. Take the enthalpy of the working fluid is given, H1 and H2 are given. So, this is the schematic of this one. The fluid is entering the compressor. The fluid here is the air. Okay, so air compressor. So, it is entering at 1 bar and 7 degrees centigrade. After the compression, the pressure increases to 6 bar and temperature increases to 127 degrees centigrade. So, there is a heat loss, so I have put a negative sign. So, in the lecture number 2 we have seen very clearly heat loss from the system is negative, heat added to the system is positive, work done on the system is negative and work done by the system is positive. Let us apply the steady flow energy equation and solve this problem. So, here I have taken the compressor as the system. Compressor is taken as the system. So, according to steady flow energy equation, so if you go by this, if you just recollect the steady flow energy equation, equation number 4 is Q plus H1 plus V1 square by 2 plus G Z1 equal to H2 plus V2 square by 2 plus G Z2 plus W. So, I have written this equation. So, let us write this one. Q1 plus H1 plus V1 square by 2 plus G into Z1 is equal to W plus instead of H1 it is H2, V1 square by 2 should be written as V2 square by 2 plus G into Z2. So, if you read the question carefully, the changes in kinetic energy and potential energy are negligible. That means changes in kinetic energy is final kinetic energy minus initial kinetic energy, that is final kinetic energy is V2 square by 2, initial kinetic energy is V1 square by 2. This is the change in kinetic energy. So, this is equal to 0. Similarly, change in potential energy, G Z2, the final potential energy minus initial potential energy is equal to 0. So, obviously these terms will not be there, okay. We will be having W term, Q term, H1 and H2. So, there are only 4 terms, 1, 2, this equation will be reduced to this one. Even if it is not given, we can assume that the changes in the kinetic energy and the potential energy are negligible. So, those terms can be eliminated from the SFE. So, here Q is equal to W plus, sorry, of course H1 is here, H1 plus Q equal to W plus H2. Let us see what we have to find out from this one. Determine the power required to drive the compressor. So, we have to find out the value of W. So, here H1 is given in the problem, H2 is given, Q is given, there is a heat, this one. So, W is equal to H1 minus H2, H1 minus H2 plus Q, okay, plus Q. So, if you substitute the values, H1 and H2 are given in the problem. So, if you see the problem, H1 is given, H2 is given, okay. So, substitute the values, you will get minus 136 and the Q value is also given minus 136.85. Minus 136.85. See, everything is kilojoule per kg, because W, small w is equal to capital W by m. Similarly, small q is equal to capital Q by m. So, this is in kilojoule and this is in kg. So, it is kilojoule per kg. Work quantity divided by mass, similarly heat quantity divided by mass. Now, we have found small w, but we have to find out the power to be expressed in kilowatt, not kilojoule per kg. So, the working fluid mass flow rate is given in the problem, that is at 0.02 kg of air is supplied for 1 second. So, now small w is equal to capital W by m. Therefore, capital W is equal to small w into m. So, small w is minus 136.85, m is 0.02. So, you will get minus 2.74 kilowatt, 2.74 kilowatt. See, this is in kilojoule per kg and this is in kilograms per second. Multiply kilojoule per kg into kilograms per second. Kilogram and kilogram will get cancelled. So, we will get kilojoules per second. Kilojoules per second is nothing but kilowatt. 1 joules per second is equal to 1 watts. Therefore, 1 kilojoules per second is equal to 1 kilowatt. So, this is the 2.74 kilowatt of power is required to drive the compressor to compress the air from 1 bar to a pressure of 6 bar, doing the process which the temperature increases from 7 degree centigrade to 127 degree centigrade. What does this negative sign indicate? The negative sign indicates the work is done because it is a power consuming device. This compressor is a power consuming device. It is not a power producing device, power absorbing device. So, the work is done on the system. Electrical energy is supplied to the compressor in order to do this process. So, work is done on the system and not by the system. So, work done on the system is negative. That is what this negative sign indicates. Now, let us move to the next numerical question. The power output of a steam turbine is 5 megawatt. The inlet and outlet conditions are inlet pressure is 20 bar and inlet temperature is 400. Initial velocity is given 50 meter per second. The datum initial Z1 is 10 meter and the outlet pressure is exit pressure is 0.15 bar. Dryness fraction is given, that is the quality of the steam at the outlet, that is given as 0.9. Velocity at the outlet is 180 meter per second and the datum, the height is at 6 meter respectively. So, these are all the inlet and outlet conditions given. Compare the magnitude of delta H, delta Ke, delta Pe, that is change in enthalpy, this is change in enthalpy, change in kinetic energy and change in potential energy, change in potential. Determine the work done per unit mass flow rate of the steam. Calculate the mass flow rate of the steam. So, this is work done per unit mass flow rate is W by M, W by M, capital W by M. Calculate the mass flow rate of the steam. So, let us solve this problem step by step. The enthalpy values of the steam is not given, which we have to take from the steam table, because the working fluid is a steam here. So, this is the simple schematic of the question which is given. The steam turbine performs the task opposite to the compressor. So, where the fluid comes in, expansion process takes place. So, that is why the profile, the geometry of the turbine should be represented like this. This is the inlet to the turbine, this is the inlet to the turbine, this is the outlet. Similarly, if you take the previous problem, this is the inlet. Compressor, while you represent, you have to represent just opposite to the turbine. So, inlet, because the pressure and temperature increases, the working fluid is compressed. So, this is the inlet, this is the outlet. Okay. Now, let us focus on the question number 2. So, at the inlet, the pressure of the steam is entering at 20 bar, 400 degree centigrade with a velocity of 50 meter per second, and it is entering at a diaphragm of 10 meter. The power, this is the power produced by the turbine. Okay. So, this is the power produced by the turbine. The pressure is at the exit of the turbine is 0.15 bar. Dryness fraction of the steam, that is, this is also called, this is the dryness fraction. Or quality of steam, small x. X2 equal to 9.9 means it contains 90% vapor and 10% liquid. That is the meaning, 90% vapor and 10% liquid. Velocity at the exit is given 180 meter per second and datum is also given. So, here like the previous numerical question where we have taken the compressor as the system, here the device turbine is taken as the system. Steam turbine is taken as the system. First, we have to find out whether what is the condition of the steam at the inlet. We know the pressure of the steam and the temperature of the steam. Is it saturated condition or superheated condition? So, that is the first task which we have to determine. For which, okay, so this is saturated water and steam table. Okay, so this is table number 2. Normally, table number 1, the temperature will be in the first column. Table number 2, the pressure values will be in the first column, and the corresponding saturation temperature will be in the second column. Okay. Now, the inlet pressure is 20 bar and temperature is 400. So, inlet P1 is equal to 20 bar, T1 is equal to 400 degree centigrade. This is the condition of the steam at the inlet. Now, from steam table, okay, from steam table at P1 is equal to 20 bar, find out the saturation temperature. So, suppose you can see here the first column is the pressure. So, at 20 bar that saturation temperature is 212.4 degree centigrade. This is table number 2. There are 5 tables in a steam table. Table 1, first column is temperature, second one is pressure. Table 2 is, the first column is pressure and the second column is the saturation temperature. Of course, specific enthalpy, specific volume, entropy values are there in both the tables, table 1 and table 2. Then table 3, 4, 5 are for superheated conditions, So, now corresponding to 20 bar, we have a saturation temperature of 212.4 degree centigrade. So, that I am going to write here 212.4 degree centigrade. Now, the given temperature of the steam is T1, the saturation temperature of the steam is T sat, 400 is greater than 212.4. Therefore, the condition of the steam is superheated. Therefore, since T1 is greater than T sat, therefore, condition of steam is superheated. So, that is what I have mentioned here at the turbine inlet, At the inlet to the turbine. Okay. So, now we have to take out the properties of the, otherwise if we do not check this condition, we will not know whether the condition of the steam is superheated or saturated condition, because the property values for this, say the enthalpy or the entropy, whatever the values we want to take, those values will vary for saturated condition and as well as for superheated condition. Now, I am going to take the enthalpy of steam at, see here 20 bar, at 20 bar pressure and 400 degree centigrade, the inlet enthalpy is 3248.7. So, how I got this value? 20 bar, see you have to refer the specific enthalpy of superheated steam, table. Table 3, 4, 5, one is for specific volume of superheated steam, one table is for specific enthalpy of superheated steam, and the last table is for specific entropy of superheated steam. So, corresponding to 20 bar pressure, this is pressure corresponding to 20 bar pressure, and this is the temperature, these are all the temperature. The given temperature of the steam is 400 degree centigrade. So, these are all the temperatures. So, corresponding to 20 and 400, you have to take the value 3248.7. So, this is the value, this is the enthalpy value at H1, 3248.7 kilojoule per kg. How I got this value? At T1 is equal to 400 degree centigrade and P1 is equal to 20 bar from superheated, for superheated condition, superheated steam. So, this is the H1 value, So, that is how it has been found, H1 value has been found. Now, for the exit condition, the pressure is given as 0.5 bar, that is the condition of the steam at the outlet of the turbine. So, now outlet of the turbine. So, the P2 is equal to 0.15 bar. And at the exit of the turbine, the dryness fraction of the steam is 0.9. That means it contains 10% liquid carryover, 90% only vapor. Now, let us go to the steam table. Corresponding to P2 is equal to, see this is the steam table 2, absolute pressure P2 equal to 0.15 bar, this is P2 pressure. I am reading the liquid enthalpy HF and the enthalpy of vaporization HFG, these two values corresponding to 0.15 bar. Read out HF and HFG 226 and 2373.2. So, HF2 is equal to 226 kilojoule per kg and HFG2 is equal to, let us see the value, 2373.2. 2373.2. All these enthalpies are specific enthalpy means enthalpy per unit mass. Specific entropy means entropy per unit mass, that quantity divided by unit mass flow rate. Dryness fraction is given. So, we can easily find out the enthalpy of the steam at the outlet of the turbine. H2 is equal to HF2 plus X2 into HFG2, X2 into HFG2. This is given. HF2 we have taken from the table, HFG2 we have taken from the table corresponding to the exit pressure of the steam at the outlet of the turbine. So, substitute the values, we will get the value of H2. Substitute the values, we will get the values of H2. H2 is 2361.9. 2361.9 kilojoule per kg. So, you can see the steam possesses an enthalpy of 3248.7 at the inlet of the turbine, and after expansion, after the steam is expanded, after it has produced, so it has lost some portion of the energy, some portion of the inlet energy has been converted into useful work, and the remaining the steam which is leaving the turbine, that is the low pressure steam which is leaving the turbine, has an enthalpy of 2361.9. So, now we will calculate one by one. The first question number 1 is change in enthalpy. Change in enthalpy. Change in enthalpy is nothing but enthalpy at the outlet minus enthalpy at the inlet, H2 minus H1. See here, if you see the diagram, inlet outlet H2 minus H1. So, that is the change in enthalpy. Change in enthalpy H2 minus H1. H2 value we have found, H1 value we have taken from the superheated steam table, H1 this is from superheated steam table, and H2 we have calculated. This formula we have to use whenever the condition of the steam is in two phase flow, like both liquid and vapor. If the dryness fraction is given, then the enthalpy has to be found out only by using this formula. Similarly, entropy of the steam also can be written like this: S2 is equal to SF2 plus X2 into SFG2. This formula should be used whenever dryness fraction is more than 0 and less than 1. Now, the second question is changes in kinetic energy. So first compare the magnitude of delta H, changes in kinetic energy. So, that is very simple formula, final kinetic energy minus initial kinetic energy. So, let me write it here. Changes in kinetic energy is equal to V2 square by 2 minus V1 square by 2. So, V2 square, both the velocities are given, final velocity is given as 180, initial velocity is given as 50. So, just a mere substitution, directly you can find out. Similarly, change in potential energy is final potential energy minus initial potential energy. changes in potential energy is equal to G into Z2 minus G into Z1. So, you can take G as a common term, G into Z2 minus Z1. So, that is what I have used. G is the acceleration due to gravity, Z2 6 minus, so you will get this one, changes in. So, this is the first one. Then, so we have found change in enthalpy, change in kinetic energy and change in potential energy, change in potential energy. Now, what is the question number 2? If you see the question, determine the work done per unit mass flow rate, that is W by M, W by M. So, according to steady flow energy equation, again we are using, there are two forms of steady flow energy equation as I told before. One is equation number 3, capital Q plus this one, 3 is in terms of capital Q and capital W, and equation 4 is dividing Q and the equation number 3 by M. That means it becomes heat transferred and work transfer per unit mass. So, capital Q becomes small q and capital W will become small w. That is the only difference. So, 3 contains with mass and 1 is dividing the equation by mass. So, we can use any one of the equation. So, I am using equation number 4. So, this is equation number 4, H1 plus V1 square by 2 plus G into Z1 equal to H2 plus V2 square by 2 plus G into Z2. Again, this is the kinetic energy at the inlet, this is the potential energy at the inlet, kinetic energy at the outlet, potential energy at the outlet, enthalpy of the working fluid at the outlet, enthalpy of the working fluid at the inlet, and that is it. So, and Q H1 plus and of course, Q will be there. Okay. So, Q plus, okay. Q term will be there. Here Q is equal to 0 for a turbine, okay. Q is equal to 0. Therefore, Q by M will be equal to 0. So, that term will get cancelled. So, which that is why I have not put it here this one, but otherwise see here you have Q is there, this is in the equation, this term is equal to 0 because capital Q is equal to 0. And substitute all the values, because all the values are given. H1 we have found from superheated steam table, enthalpy of the superheated steam, V1 is given, G is at 1, V2, H2 we found using HF2 plus X2 into HFG2, then Z2 is given. So, find out the value of W, find out the value of W. This W is equal to capital W by small letter m, work transferred per unit mass flow rate of the working fluid. So, that is a very simple one. And the third one is calculate the mass flow rate of the steam, mass flow rate of the steam. So, we know the work done by the system per kg of steam supplied, and we know the total power produced, we know the total power produced. When we divide the total power output of the turbine divided by W, the work done by the system. So, see here if you see M is, let me write it here, power output of the turbine divided by work done. So, this is in kilowatts, this is kilojoule per kg. So, kilowatts is kilojoules per second divided by kilojoule per kg, kilojoule and kilojoule will get cancelled. So, you will get the mass flow rate, it is m dot, it is m dot kg per second. I have represented in some places the mass flow rate as m, but actually it is m dot. Because of the system compatibility, I have used the symbol m. Wherever it is there, it is not kg, it can be kg per second also, but actually the correct representation is m dot. So, m dot we are getting in kg per second. So, 5 megawatt. So, 5 into 10 power 6 convert the megawatt into watts, that is joules per second, into 10 multiplied by 10 power 6, mega is 10 power 6 divided by the work done. So, that will give you, to achieve this process, 5.7 kilograms of steam to be supplied for 1 second per second. So, that completes the problem number 2. So, we have asked to find the mass flow rate of the steam. Now, let us move to the third numerical question. Steam at, so the first problem was based on how to apply the steady flow energy equation for a compressor. The second problem which we have seen just now is application of steady flow energy equation for a steam turbine, and the third example which I have taken is for a nozzle. Steam at a pressure of 6 bar and 200 degrees centigrade enters a nozzle which is insulated with a velocity of 50 meter per second. It leaves the nozzle at a pressure of 1.5 bar and velocity of 600 meter per second. See the initial velocity of the steam, it is 50. See the exit velocity, it is 100. As I mentioned before, the function of the nozzle is to enhance the velocity of the working fluid. So, here it is increased by 12 times. It is increased by 12 times from 50 meter per second to 600 meter per second. And of course, there will be a drop in pressure. So, the pressure is reduced from 6 bar to 1.5 bar, reduced to 1/4. Determine the enthalpy of the steam at the exit of the nozzle, neglecting the changes in potential energy. We cannot neglect the changes in kinetic energy of in case of a nozzle and a diffuser, because in nozzle and diffuser one property increases at the expense of other property. That is, in nozzle the velocity increases at the expense of pressure, that is pressure drop takes place. So, we cannot neglect the changes in kinetic energy. V1 will be there, V2 will be there. So, V1 square by 2 and V2 square by 2 cannot be neglected. Now, this is the schematic of the nozzle. The steam is entering at a pressure of 6 bar and temperature T1 is 200 degrees centigrade, velocity is 50. So, this is, as I said before, nozzle does not have any this. You can see the varying cross section area. You can see the area here at the inlet of the nozzle as the working fluid, see the area here, see the area this and see the area here. So, it is a converging type of nozzle where the area gradually decreases, If it is a diverging, it will be like this, just opposite to that one. So, the pressure at the exit of the nozzle is 1.5 bar, velocity has increased to 600. This is the data given in the problem. Now, let us solve this problem. So, like the previous two cases where compressor and turbine has been taken as the system, nozzle is considered as the system. So, now let us solve this problem. Inlet pressure is 6 bar, temperature is, let me see the temperature value, 200 degrees centigrade, velocity is 50 meter per second. This is the inlet condition. So, similar to the previous problem, we do not know whether the condition of steam is saturated at the inlet or superheated at the inlet. As how we found for the previous problem, we have to find out the saturation temperature for the steam at the inlet. So, from steam table, that is table number 2, because corresponding to the given inlet pressure we are going to find T sat. So, use table number 2. Let me write it clearly. Table number 2, at P1 is equal to 6 bar, what is T sat? The saturation, let us go to the steam tables. Here, this is saturated water and steam table, pressure table. This is actually a continuation of table number 2. Corresponding to 6 bar, column 1 is pressure, 2 is T sat, saturation temperature corresponding to the pressure. So, the saturation temperature is 158.8. So, all these values are in degree centigrade. So, 158.8 0.8 degree centigrade. Given temperature, the temperature of the steam at the inlet is 200 degree centigrade. So, T1 is greater than Tsat. What does it indicate? Condition of steam is superheated. If the temperature of the steam at the inlet is more than the saturation temperature, that means the condition of the steam is above saturation, that is superheated condition. Heating the steam beyond saturation is superheated, and if it is below saturation, it is called subcooled state. So, these are all the normal basic terms which are used. So, here the condition of the steam is superheated, like previous example, superheated at the inlet of the nozzle, at the inlet to the nozzle, at the inlet to nozzle. This condition is only applicable at the inlet of the device which is under attention. So, here it is a nozzle. So, the condition of the steam is superheated. Okay. Now, like for the previous problem, we are going to find out the enthalpy of the steam at the inlet. So, we have to go to the superheated condition table. So, from steam table, at P1 is equal to 6 bar, T1 is equal to, we have to find out the property at given temperature only, not for the saturated condition. The saturated condition to be taken only for checking whether the steam is superheated or saturated or not superheated, okay, or it may be, it will be, if it is not superheated, it will be saturated. So, for the given condition, now I am going to take the value from the steam table. This is pressure is 6 bar, this is specific enthalpy of superheated steam, specific enthalpy of superheated steam. So, corresponding to 6 bar, this is the temperature of the steam is 200, see here temperature is 200, pressure is this one. So, I am reading in case of the previous problem, the temperature of the steam was given as 400. So, that is why I taken this value. So, to make you understand easily, let me put an arrow. So, this is for the present problem, example number 3. The temperature is given as 200, pressure is given as 6 bar, you take the intersection one. So, you can read the value 2849.7. So, this is the enthalpy of steam at inlet of the nozzle, 2849.7 kilojoule per kg. This is the superheated enthalpy of steam at inlet, 2849.7. Okay. So, this is what I have found here, 2849.7. Now, let us write the steady flow energy equation. Q by m plus or this is nothing but small q H1 plus V1 square by 2 plus G into Z1 equal to H2 plus V2 square by 2 plus G into Z2 plus small w. Okay. Now, let us see the problem. Steam at 6 bar enters a nozzle which is insulated. When a device is insulated, that means there is no heat transfer. Q is equal to 0. Capital Q is equal to 0. that means small q equal to capital Q by m, that also will be equal to 0. So, this term will get cancelled. Next, if you look at the problem, neglecting the changes in potential energy, neglecting the changes in potential energy, neglecting the changes in potential energy. That means delta PE is equal to G into Z2 final potential energy minus initial potential energy. So, this is equal to G into Z2 minus Z1 is equal to 0. So, this term and this term will get cancelled. This term and this term will get cancelled. So, now we are left with H1 plus V1 square by 2 plus equal to H2 plus V2 square by 2 plus W. So, in case of a nozzle, so the inlet fluid velocity is increased while the fluid leaves the nozzle, the pressure drop takes place. So, there is no heat quantities involved or there is no work quantity involved. So, W is equal to 0 for a nozzle. When W is equal to 0, that is small w, therefore, small w is equal to capital W by m, which is equal to 0, which is equal to 0. So, substitute these values. So, this term also will become 0, this term also will become 0. Now, we are left with H1 plus V1 square by 2. There are only 4 terms, 2 terms on the left side. So, this equation will reduce, this equation will reduce to the steady flow energy will reduce to H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. H1 is we have determined from the specific enthalpy of superheated steam from the steam table, that is 2849.7. So, substitute the value 2849.7 plus what is the initial velocity? The initial velocity is given as 50 meter per second, initial velocity is given as 50 meter per second. 50 square by 2, that is equal to right side, this is H2 we have to find out, determine the enthalpy of the steam, this is enthalpy of the steam at the exit of the nozzle. So, H2 is unknown plus exit velocity is 600 meter per second, 600 square by 2. So, rearranging and calculating, you will get (2670), that is 2671 kilojoule per kg. So, if you round off, H2 is equal to 2671 kilojoule per kg. This is the enthalpy of the steam leaving the nozzle, enthalpy of steam leaving the nozzle. In order to have the units balanced on both sides, that is left hand side as well as right hand side. See here, if it is, this is in kilojoule per kg, this is the, enthalpy is in kilojoule per kg on left side as well as on the right side, but this is in meter per second. So, to have the uniform this one, so you have to divide by 10 power 3, that is 1000. Here also you should have into 1000. So, let me explain here itself. See, this is to be there for the velocity term, So, then only otherwise the answer will be different. So, this is V square, V1 is 50 meter per second, V1 square is 50 square by 2 into 1000, because this quantity has got there is a summation term involved. So, to have uniformity in the unit on both sides. So, divide by 1000 on the energy, kinetic energy tau. So, this is the enthalpy of the steam which is leaving the nozzle, and you can see the inlet enthalpy is 2849. So, 2849, there is a drop in enthalpy, So, that completes the problem. So, to summarize what we have discussed in this lecture number 3, we have seen what is a steady flow process, that is what is the mass balance, how to do the energy balance. Mass balance is the mass entering into the system is equal to mass leaving the system. Total energy content of the system remains constant. Energy in is equal to energy out. And we have derived the steady flow energy equation. There are two forms of steady flow energy equation. One is with capital Q and capital W. When you divide that equation by the mass of the working fluid, we get small q and small w, that is heat transferred and the work transfer and the work quantities per unit mass. And we have applied the steady flow energy equation. Of course, it can be applied for more than the examples which we have seen. We have seen 3 examples. One is how the steady flow energy equation is applied for a compressor, air compressor, how it is applied for a turbine, and the third one is the nozzle. So, with that I conclude this lecture number 3. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.